So in this session on signals and systems, we are going to study an example of obtaining expression for convolution. The convolution integral we have already studied last time, and we would now like to see how to use that expression in order to obtain the expression for the output. Now, let me repeat the definition for the convolution integral which we studied last time. So xt and ht are the two inputs for which the convolution is to be obtained. So you use a dummy variable. First replace t by tau. So you'll get x tau. Then use ht minus tau, which corresponds to inversion followed by delay. Multiply the two and then integrate over all time and you get the output. Now I would like to point out one thing to you, that when we developed convolution integral, we were basically talking about finding the output of a system given the input. And our argument was that whatever may be the nature of the input, if the impulse response of the system is known, then you can calculate the output. However, note that this is basically a mathematical operation on two functions. Therefore, this is not the only application of convolution, that of finding the output of a system. Convolution also has other applications, for example, in the areas of image processing, probability studies, etc. Okay, having said that, let us now return to this problem of solving the convolution integral. So last time we had studied the steps and we had said that the first step was to replace t by tau. So you'll obtain x tau and h tau. And let us now focus first on obtaining this ht minus tau, which is essentially inversion followed by the delay. So this is what we study first. So let us take one example of ht. This could have been some other kind of pulse, but let's say it's like this. Now the first thing we do is replace t by tau. So essentially you get the same function, but instead of being a function of t, it is now a function of tau. So h tau can be drawn like this. So it is just a triangular pulse which starts at 0 and becomes 0 at tau equal to 2. Now we invert this. That means around the y-axis we perform the rotation of 180 degrees. So instead of starting from 0 and ending on 2, it will start from -2 and end on 0. That's how it will look. This inversion we have studied before, and h of minus tau will look like this. Now you have to delay this by t. So the whole waveform shift to the right by t and look something like this. Now this point, this 0 point becomes t. Therefore this point on the graph essentially becomes t minus 2. Remember, if this is 0, this is minus 2. So if this shifts to the right by t, then clearly this is going to be t minus 2. And when we are evaluating convolution, what we are doing is we are shifting it to the right and shifting it to the left, and then obtaining the expressions for product and integrals. All right. So this is how we obtain h of t minus tau. So you may shift it to the right, you may shift it to the left, and so on. All right. So having studied this, let us now take one specific example. So in this example, xt is equal to e raised to minus at ut, where a is greater than 0. That means it is positive. So if this is greater than 0, it means that this is an exponentially decaying function. This is how it will look like. And multiplication by ut ensures that for values of time less than 0, xt is going to be 0. That is the meaning of this multiplication by ut, because remember, ut has a value of 1 for times greater than 0, and for times less than 0 it is equal to 0. If this is not present, then this e raised to minus at, as t becomes negative, this will simply go on increasing in the other side. So that is your xt. What about ht? Let us assume that for this example, ht is a unit step function itself. Okay, and the problem as usual is to find xt star ht, that means xt convolved with ht. All right, so let us first uh, change t to tau, so h tau becomes u tau, so it is basically a unit step function. Now you have to invert this, so h of minus tau inverted will look like this, and then you have to delay it by t. Okay, but before we do that, just note that just as you replace t by tau for the second function, for the first function also you replace t by tau, so this becomes x tau equal to e raised to minus a tau u tau, and now you are ready to delay this function. So this can be delayed for various values of time. Right now the delay is shown such that t is less than 0, so it's actually advanced. Now when t is less than 0, if you look at these two functions, you find that they are not overlapping, which means that if you take their product, it is always going to be 0 for all values of tau. For example, if you consider values of tau less than t, this is finite, but then x tau is 0, so product will be 0. Now if you consider values of tau greater than 0, then this is finite, but this function is 0, so the product is going to be 0. So as long as t is less than 0, the convolution is always going to be 0 because the product is 0, nothing to integrate. All right, so what we'll do is we'll now increase this time to a point where both the functions start overlapping. So let me show that diagram to you. So now t is greater than 0, and now you will find that this is the time period from, that is tau equal to 0 to t. In this range the functions are overlapping, and note that this impulse response here has a value of 1. So when we take the product, it is essentially the function of x tau itself, because this multiplied by 1 is going to be this function itself. So that is just the exponentially decaying function. And note that for values of tau less than 0, this is 0, so the product is 0. And for values of tau greater than t, this is 0, so again the product is 0. So when you evaluate the convolution integral, the essential limits are for tau from 0 to t. So let us write that integral now. For t greater than 0, e raised to minus a tau multiplied by 1, because remember in this 0 to t range, when tau lies between 0 to t, your unit step function has a value of 1. So it is essentially this which has to be integrated with respect to tau and put the limits, so you will get a function of tau, function of t. All right. So if you integrate, we know that this minus 1 by a e raised to minus a tau with the limits 0 to t. So when you put the limits, you get this expression. So this is essentially, so here as t goes on increasing, this will go on decreasing, and you will get an increasing function. So although one of the waveforms was a decreasing exponential, when we obtain the convolution with respect to unit step, we get a result which is an increasing exponential with respect to time. Incidentally, note that this has a value which is 0 for values of time less than 0. Therefore, the complete expression for this for all time we can get by multiplying this by ut. So this ensures that for t less than 0, the yt has a 0 value. So we have seen one example of how to obtain the expression for the convolution. In a succeeding couple of sessions, we will continue the study of convolution, see other examples, and also see how to write the MATLAB code for obtaining the convolution of continuous time systems. But for now, that's all.